today is a continuation of former lecture, but as usually I prefer not one. More students. Okay. So let me call this section, let it be differentiation. And integration of power series. Okay, very good. So here firstly I'll recall what we consider. We consider power series, real power series now. So x naught, a naught, a1, a2, so on are real numbers. Real numbers. So we'll talk about term by term, differentiation and integration of power series. So let me make a tag and suppose one has a positive radius of convergence capital R. Denote f of x equals to the sum. So we know it is defined at least for those values of x. Then, first, f of x has derivatives of arbitrary order at any point x which satisfies the inequality modulo x minus x naught less than capital R in modulus, which can be obtained by term differentiation of 1. Second assertion. The integral from 0 to x f of t dt, we know it exists because of continuity of f of t. We know this property. So the integral for x, again, satisfying the inequality x minus x naught less than r, can be obtained by term integration of 1 on interval 0x. Of course, here for x negative, it's better to remember our agreement to change. If x is negative, then 0x, it's better to consider x 0, right? And integral should be taken with minus. Then third, all series in first and second assertions have the same radius of convergence r as in 1. So same radius of convergence we have. And last assertion, coefficients can be obtained uniquely. So an equals to nth derivative at 0 over n factorial, n equals to 0, 1, not at 0, at x naught, sorry, 0, 1, 2, and so on. So these are 4 assertions. So once we have a power series with positive radius of convergence and denote its sum like that, then coefficients can be deduced by this formula. So proof. Third was proved at the end of 24.1. When we will get the PM. I asked yesterday the author of our lecture notes, and still I don't understand why maybe he will send you the topic. But I would say mostly I follow Zorich textbook, especially, and also so it's a kind of mixture between Zorich and how it is called Baby-Rudin principles of mathematical analysis. So, at the very end of the last section, there was an assertion which says that when we differentiate term by term a power series, the radius of convergence will be the same. So we apply several times, it gives the same radius of convergence for derivative of arbitrary order, and if we apply it to inverse operation, then we obtain for the integral, because if you differentiate the integral, then as we know by Newton-Leibniz formula, we obtain the original function f of x after differentiation. So, okay. Now, what we need to prove? We need to prove that we can, in fact, obtain the integral and derivatives by term differentiation. And in fact, for example, second assertion follows from two theorems. One of them, theorem from yesterday's lecture about uniform convergence of power series, and theorem about uniform convergence and integration of functional series. This was before. So let me recall those two theorems, better to say what I want to take from them. So uniform convergence of power series says that once we have a power series, one, right? Then it converges uniformly on arbitrary interval, closed interval, which lies inside the interval of convergence. In fact, yeah, inside the interval of convergence. In fact, it said about uniform convergence inside the disk of convergence. But so we were talking about disk of convergence, right? But now we are interested only in real numbers. And it means that when we are in disk of convergence, in particular, we have uniform convergence at every closed interval inside this disk. In particular, every interval like 0x, where x is somewhere here, like here, right? Oh, sorry. I'm sorry, not from 0. From x0 to x, of course. And here also x0. That is misprint. Very sorry. Sorry. Yeah. No, it's not. Okay. So, first theorem says that our series 1 converges uniformly on the interval x not x. Okay. Next theorem, uniform convergence and integration, says once we have a functional series and every term of this functional series is integrable on an interval, so three conditions. Every term, two conditions, sorry. Every term is integrable on an interval and functional series converges uniformly. Two conditions. Then we can integrate term by term. That is what was said in that theorem about uniform convergence and integration of functional series, right? So now, look, on the interval x not x, we have uniformly convergent series. Every function an times x minus x naught power n is integrable because it is continuous. And hence, all conditions of that theorem are satisfied and we can integrate term by term. So it means that indeed the integral can be obtained by term integration of 1. Okay. Second condition is right. Analogously, the first assertion follows once again from the same theorem, from theorem about uniform convergence. Of power series. So once again we apply that assertion from former lecture, and another theorem, uniform convergence and differentiation of functional series. Theorem about differentiation of power of functional series asks more. So there are three conditions to be checked to be able to use that theorem. Which conditions? Firstly, every function should be differentiable. Look at our functions. We have power functions. They're differentiable everywhere. Second condition, series converges at a point. We know more, it converges at every point of the interval modulo x minus x naught less than capital R. And the third condition, differentiated, or better to say series of derivatives. Converges uniform. How to check the last condition. So, look, we combine the assertion which was proved at the very end. So, what we know? If we differentiate term by term, we obtain again a power series with the same radius of convergence, right? So, the series of derivatives is a power series with the same radius of convergence. Then, this theorem about uniform convergence of power series says that series of derivatives converges uniformly, right? Okay, so this condition is checked. And once we have all of those suppositions are satisfied, we know, then we apply that theorem which says that indeed we can differentiate term by term. And we can apply it as many times as we want. So we deduce the first condition, the first assertion, that is, right? Okay, the last, now the very last formula for coefficients. Let's start with very first, A0, how to obtain it. But it's obviously f at x0. Why? Because look at the definition of f of x. If you substitute here x equals to x0, what happens? X equals to x0. We have zeros, and of course we agree that when n is positive, then 0 in positive power is 0. And for n equals to 0, another agreement, power 0 means we have 1, right? So it means all terms of our series are equal to 0 except for n equals to 0. So we obtain that formula. And that is precisely what was written. Recall our agreement, 0's derivative is the function itself, 0 factorial is 1. So that is precisely what was written. Okay, now look, by the first assertion, we can differentiate term by term. So we can write the formula, so we differentiate term by term. What we will obtain? An. So we differentiate x minus x0 power n k times. So first differentiation, what it gives? N times x minus x0 power n minus 1, right? First differentiation. Second differentiation, n minus 1, right? And so on. So every time when we differentiate, we have a multiplier which corresponds to the power. So how many multipliers we obtain? As many as we differentiate, right? Every differentiation gives a multiplier. So we obtain k terms at that product. It means the very last will be n minus k plus 1. So then we have precisely k k multipliers, right? And what is about exponent also should be n minus k, right? Then when we start, of course, first term, for example, if we differentiate once, then n equals to 0, term with n equals to 0 is constant. N equals to 0, no power. When we differentiate, it disappears. It is 0, right? Constant term after differentiation is 0. So, one term disappears after first differentiation. And it will happen every time, right? So, we start from precisely k. That is the result of term by term differentiation of 1. K times. K times. Okay, then what we do? We substitute. Substitute here x equals to x naught. What we obtain if you substitute x equals to x naught? Once again, every term at this series equals to 0 except for n equals to k, right? So what remains? F kth derivative at x naught equals to, okay, let me write it here. F kth derivative at x naught equals to ak times n equals to k, right? So k times k minus 1 and so on. So if n equals to k, the very last is 1, right? And that is 1 when n equals to k. And what is it, this product? All natural starting from 1 up to k. That is k factorial. So we deduce our formula. Instead of n, k is written, right? So fourth assertion is proved as well. Okay. That is what I wanted to include into the last section, but I was not able to do it. So, now next section. Point 2, sorry, Taylor series. So I'll start with definition. Definition 1. We say f is infinitely differentiable. Infinitely differentiable. At x naught if fnth derivatives at x naught is defined for all natural n. So infinitely differentiable means differentiable as many times as we want. Doesn't mean that derivative is infinity, no. It's defined, of course, in R. Finite derivatives only are considered, not infinite. So, and now once we have an infinitely differentiable function, then we can determine coefficients. So next definition 2. If f is infinitely differentiable at x naught, then Taylor series of f with center x naught is defined as follows. Sum n starts from 0 up to infinity, and derivative at x naught over n factorial times x minus x naught power n. So, let me explain the difference between general power series and Taylor series. So, look, when we have general power series, what we know? So, general power series is a series of this kind, right? Where n are some coefficients. Real or complex doesn't matter. Now, we know from former theorem that if radius of convergence is positive, right, then this has a sum, let's say s of x, right? And then how we may compute coefficients? Coefficients are precisely like that. So, look, once again, given power series with positive radius of convergence, we can denote the sum of this power series like that. Then automatically coefficients can be computed by that formula, right? But now we go in opposite direction. So we have a function which has all derivatives at a point x naught, right? Then we can determine coefficients like that, right? And we call this power series a Taylor series. So it seems practically the same, right? But no, there is a difference. And to show that there is a difference, let me give an example. So example 1. Consider such a function. F of x equals to e to the power minus 1 over x squared for x not equals to 0 and 0 if x equals to 0. So the essence of this example is the following claim. That is the claim. So look, what it means. Firstly, I want to explain the meaning of this example. Look, we have a function. It is well defined, right? Obviously, this is not a zero function. In fact, it is zero only at one point, right? And it is not zero at other points. But what happens? It turns out that when we construct Taylor series for that function, right? So how we should construct it? Instead of x naught, I take 0. X naught is 0, right? So all coefficients, we know that all derivatives at 0 are zeros, right? So it means that Taylor series for that function is identically 0, right? So Taylor series, then the Taylor series for f of x is identically 0. What it means? It means we construct a Taylor series, but the sum of this series will be not f of x, right? It will be completely different. If you sum zeros, what we have? 0, right? Identically 0, right? So it means that the sum of Taylor series need not to be equal the function f of x itself, as one could expect, right? So, moreover, it doesn't depend on the radius of convergence. Look, our Taylor series contains only 0 terms, right? It means radius of convergence is infinity, right? It converges everywhere. The series 0 plus 0 plus 0 plus 0 and so on, right? Converges everywhere. So radius of convergence is infinity. It converges everywhere. But nevertheless, the sum of this series is different from the function which generates the Taylor series. So that is the meaning of this example, right? Okay, so let's start to prove the claim. So proof of the claim. N equals to 0, what? F0's derivative is precisely the function, and it is 0 by the definition, right? So the first is obvious. Okay, that is concerning the list of the theorems and questions. Okay, I'll finish with examples, and then I'll talk about written example. So Okay, we continue. And you see, for n equals to 1, the first derivative, how can be obtained? It can be obtained only by definition. So we need to consider the limit as delta x tends to 0 of the difference 0 plus delta values of our function at 0 plus delta x and at 0 divided by delta x. So increment of function divided by the increment of the argument, right? So what we know what is f at 0. So we can compute the limit directly. That is e to the power minus 1 over delta x squared over delta x. And how to proceed here? I would say the best is to replace 1 over delta x, replace it by t, let's say, right? Then t tends to plus or minus infinity. So we have limits simultaneously t tends to plus or minus infinity, right? Both infinities should be considered simultaneously, and we have t times e to the power minus t squared. And then I can rewrite it like that. And then it is clear what is going on. At the moment we have infinity over infinity, right? And we have L'Hopital rule, right? Use L'Hopital rule. We have then limit t tends to plus or minus infinity 1 over 2t times e to the power t squared. And now it is clear what is the result. We have infinity in denominator, 1 in numerator, that is 0, right? So, and you see this is not so simple, right? Computation of the first derivative at 0. And we need to compute all derivatives. And the only possibility is to use the definition. So we need somehow to represent all derivatives of our function at other points, right? So let us try to do it. So let's try to compute f prime at x for non-zero x. What happens? If I differentiate e to the power minus 1 over x squared, then by the chain rule we have expression like that, and it gives 2 over x cubed times e to the power minus 1 over x squared. Of course, for non-zero x's. So it means we determined completely what is f prime of x. I can write now f prime of x as a function is the following. X not equals to 0, 0 if x equals to 0. F prime at 0 we computed just now, right? So, now we understand what we have to do to prove this claim. I wrote first derivative, right? So analogously we differentiate second, third, and so on. And you understand it's impossible to write down explicitly the formula for arbitrary derivative, right? What we are interested in the last line, the value at 0, that is important for us. But what we can remark, look, let me try to differentiate once more. Second derivative, right? For non-zero, 2 over x cubed e to the power minus 1 over x squared. I should differentiate this expression. It gives what? Derivative of product. So minus 6 over x power 4 e to the power minus 1 over x squared, and then plus 2 over x cubed times derivative of exponent. Derivative of exponent was given by this expression, 2 over x cubed e to the power minus 1 over x squared. And that is all together, I can rewrite it as follows. 4 over x power 6 minus 6 over x power 4 e to the power minus 1 over x squared. So you see, expressions become more and more complicated, right? But what is important? So now another claim to prove. So what I want to prove now another claim as derivative at x equals to a polynomial of degree 3n at 1 over x times e to the power minus 1 over x squared for x not equals to 0, where p3n of t is a polynomial of degree 3n with leading coefficients leading coefficient 2 to the power n. Look, that is a formula which unifies both expressions, that one and this one, right? So, for example, look, what is P3 of t is 2t. Look, n equals to 1. N equals to 1. N equals to 1. P3 of 1 over x, right? P3 is that one. If you substitute instead of t 1 over x, you have 2 over x, cube, yeah. 2 over x cube, right? 2t cube, right? Then, what is P6 of t? Look here, that is 4 t power 6 minus 6 t power 4. Look, polynomial of degree 6, right? Leading coefficient 2 to the power 2, 2 squared, right? So, for n equals to 2, it is also true, right? So that is how we unify those two particular cases. And there is a general formula, right? which can be proved by induction. So, proof of this claim by induction. By induction. So, n equals to 1 we checked. Proven. Right? Proven. So, if we suppose n equals to k is valid, right? So, check n equals to k plus 1, right? So, I want to compute derivative k plus 1, right? K plus 1 order. That is derivative of kth derivative. I take kth order derivative and then differentiate. Kth order derivative by the induction hypothesis, right? I can use it. So, P3k of 1 over x times e to the power minus 1 over x squared prime. Right? We differentiate. Now let's differentiate. We have product. So I need to differentiate first term times exponent plus P3k of 1 over x times derivative of exponent, I computed, so 2 over x cubed times e to the power minus 1 over x squared. So, what is it? Let me unify. Derivative of polynomial, that is derivative of the polynomial, right? In fact, that is not a polynomial, that is a rational function, right? Polynomial of 1 over x. We differentiate it by chain rule, so we obtain derivative of polynomial, right? P3k prime at 1 over x times minus 1 over x squared by chain rule, that is this derivative, plus P3k of 1 over x times, times 2 over x cubed times e to the power minus 1 over x squared. So, what I have to check? I have to check that what is written in brackets is precisely P3k plus 1 of 1 over x. So, let me check. So, that is what I want to check. Look, what is written here? P3k plus 3, right? So, that is a polynomial of degree 3k plus 3 with leading coefficient 2 to the power k plus 1, right? Look, what we had here, that is a polynomial of degree 3k with leading coefficient 2 to the power k, right? I multiply by this one. So, leading coefficient was 2 to the power k. Let me write down what is leading term of that expression. 2 to the power k over x to the power 3k, right? That was leading coefficient of our polynomial, 2 to the power k, right? Times t to the power 3k, I substitute instead of t 1 over x, right? That is written here. So look, that is leading. largest degree of 1 over x, right? Largest degree. I multiply it by that one. What I obtain? 2 to the power k plus 1 divided by x to the power 3k plus 3. Precisely what should be here, right? What remains? Okay, are the powers of 1 over x are smaller, right? For example, 1 over x power 3k minus 3, maybe, or 3k minus 1 even, doesn't matter, right? We multiply 3k minus 1 plus 3 is 3k minus plus 2, right? 3k minus 1 plus 3. 3k plus 2, right? 3k plus 2 is strictly less than 3k plus 3, right? So, all other powers of 1 over x in this expression, or other powers, are less than 3k plus 3. What happens here? Polynomial of degree 3k. Take derivative. That is a polynomial of degree 3k minus 1, right? If you differentiate polynomial of degree 3k. So, polynomial of degree 3k minus 1 and which power of 1 over x? Second power, right? 3k minus 1 plus 2, that is 3k plus 1, right? 3k plus 1 less than 3k plus 3, right? So, indeed we have precisely polynomial of degree 3k plus 3 of 1 over x with leading coefficient 2 to the power k plus 1. So, this claim is proved. This claim is proved, right? Okay, now I return to my main claim. Main claim. That one. As derivative at 0, right? Once again, so once again, proof of this claim by induction. So, n equals to 1, we checked, right? First derivative we checked. N equals to 1 is done, right? So, okay, suppose if kth at 0 is 0, n equals to k is valid, right? So, we need to compute derivative of the order k plus 1, right? And we proceed by definition. So, that is derivative of kth order for x equals to 0, right? We need to compute derivative of kth derivative and divide it, take it at x equals to 0. Let's compute it. By definition, limit as delta x tends to 0, kth derivative 0 plus delta x minus kth derivative at 0 over delta x. Okay, we know by hypothesis induction kth derivative at 0 is 0, right? And kth derivative at delta x may be computed by former claim, right? So, I have limit as delta x tends to 0. substitute polynomial of degree 3k at 1 over delta x times e to the power minus 1 over delta x squared over delta x. Okay, once again, like we did before, denote 1 over delta x by t. So we have limit as t tends to plus or minus infinity, right? And then what I have? P3k of t times t divided by e to the power t squared. And now look what happens. That is a polynomial of degree 3k plus 1, right? So that is 0 y, since limit as t tends to plus or minus infinity t to the power m over e t squared is 0. Because if we have a polynomial, right, we have a sum coefficients times t to the power. Doesn't matter which power. If we know that t to the arbitrary power divided by e to the power t squared is 0, then the result, finitely many terms here, is 0. Why this is the case? Substitute here t squared equals to y. Then what we have? Then we have limit as y tends to infinity, y to the power m over 2. Of course, I need to put modulus here, otherwise I'll get some problems, over that is equal to e to the power y, right? And then what happens? That is either integer or integer divided by 2, right? So I apply L'Hopital rule. What happens if I apply L'Hopital rule? That is limit as y tends to infinity m over 2 times y power m over 2 minus 1 over e to the power y. And what happens then? If m was equal to 1, then what happens? 1/2 minus 1 is minus 1/2, right? It means square root of y is in denominator, so it is 0, right? If m equals to 2, 0th degree means 1. But once again, infinity in denominator, so it's 0, right? If m is greater than 2, then we continue, right? We apply L'Hopital rule once again, and so every time degree is small and smaller, right? But denominator doesn't change. E to the power y, right? So finally, for arbitrary m, right, we'll obtain 0 after several applications of L'Hopital rule. So the main claim is proved and example is finished, right? Okay. It was not easy, but that is very important thing. So you see, for example, yeah, we can change it a little bit. For example, put here greater than 0, right? Then what happens? The graph will be, for this function, the graph is like that. For our function, the graph is like that. So if x goes to infinity, we have minus 0, 1, right? So that is like that, something like that. The graph of our function is as follows. Right? So you see, here what happens? That is so flat that all derivatives of arbitrary order here are equal to 0, right? It means that, for example, I may replace it like that. So y equals to e to the power minus 1 over x squared. X is positive, 0, x less or equal to 0, right? And what happens with that function then? This function has derivatives of arbitrary order at every point, right? And you see what are properties. It is identically 0 here, but it is not 0 for positive, right? So this is very, very smooth function. Extremely smooth, I would say, because it has infinitely many derivatives, right? That is quite important behavior. Okay. Later we'll use more functions of this kind, but now, okay, I have 10 minutes, so maybe I'll finish. So, as I promised, after the example, topics for written exam. So, written exam. As we know, it will be 18th of June, right? 18th of June. 90 minutes. 90 minutes. It will be distant. And you have 6 questions, 6 problems. First one, construct a graph in fact rational function is considered here only. Second, compute an integral. Once again, of a rational function. Third question, study absolute and conditional convergence of an improper integral you should study very carefully here the example integral from 0 to infinity sine x over x power alpha, for example, right? Because when it converges conditionally, when it converges absolutely, for which values of alpha, and so on, right? Written exam costs 30 points. 30 points, like what you will get during semester, the whole semester, 30 points. Oral exam, 60 points. And then there is a scale from 0 up to 120 to translate it into 10 points scale. Okay, fourth question. Study convergence of a series. Use Cauchy test. Just Cauchy test, so limit of nth root of an. Fifth, study uniform, pointwise and uniform, pointwise and uniform convergence of a functional sequence. On two sets, 0, 1, let's say 1, infinity. And sixth, study pointwise and uniform convergence of a functional series. Again, uniform converges on 0, 1 and 1, infinity. So, for one of them you have uniform convergence, for another you haven't uniform convergence. So, you need to prove when you have uniform convergence, when you haven't. That's it. I plan to make a scale. So price for each question will decide that the sum will be greater than 30. And then, yeah, written exam will be online. I said distant. Online, yeah. So, then I plan to collect the results, your results, and then to translate the sum. It will be approximately 35 or 36 maximum, right? To the grade from 0 to 30 with legs. You understand? So, for example, which grades for the written exam are possible? 30, 20, 6, then 22, something like that, right? So not every number from 0 to 30 is possible, because there will be a translation to make some lag between students because of written exam. Okay? And it will be determined after the information about the total process of writing. So it was usually also for Russian-speaking students before, but now they simplified it and made just 30 points, and all numbers are possible. I prefer to make difference a little bit more definite. I mean, before oral exam, the difference should be more definite from my point of view. But of course, maybe next time it will be different, I don't know. So for a while, that is the first time when there is a written exam for English-speaking students, in fact. So the first experience, okay. Of course, no questions for oral exam. Oh, sorry. For oral exam, I'll prepare questions a little bit later. For a while, I prepared questions for written exam because it is before oral. Okay. So I think we can stop now.